Mercury, only slightly larger than our Moon, is the smallest planet in the solar system, nearly 20 times less massive than Earth. Located just 0.4 astronomical units from the Sun, it basks in sunlight nearly 3 times more intense than on Earth, and our star appears significantly larger in its sky. With virtually no atmosphere to shield its surface, Mercury experiences extreme temperature swings, though it does not hold the absolute record. That distinction belongs to Venus. Completing a full orbit in just 88 Earth days, it is the fastest planet in our solar system. The Messenger mission revolutionized our understanding of Mercury. Orbiting the planet, it revealed strange ridges and scarps, indicating that Mercury has contracted by about 7 kilometers since its formation. Over 4,100 orbits and more than 270,000 images provided an unprecedented portrait of this rocky world. Near the poles, regions permanently in shadow host water ice, hidden within deep craters despite surface temperatures that can exceed 400 degrees Celsius under direct sunlight. Unlike our Moon, Mercury's surface is not dominated by phosphate-rich rocks, but features sulfides and other minerals, suggesting it formed under very different conditions. The planet's partially molten metallic core generates an asymmetric magnetic field, allowing the solar wind to strip atoms from its surface, a process that feeds Mercury's tenuous exosphere. Venus, often called the morning star or the evening star by ancient sky watchers, is a planet that both fascinates and intimidates. Second from the Sun, it is nearly Earth's twin in size, mass, and density. Yet beneath its dense, swirling clouds lies a world utterly unlike our own. Venus is shrouded in a crushing atmosphere dominated by carbon dioxide, with thick clouds of sulfuric acid droplets that reflect and scatter sunlight, making the planet exceptionally bright in our sky. This heavy atmosphere drives an intense greenhouse effect. Water that may once have existed on the surface slowly vaporized, trapping heat and preventing escape, raising surface temperatures to an average of 460 degrees Celsius, hot enough to melt lead. Without plate tectonics or efficient heat dissipation, Venus's surface has remained stagnant for millions of years. Its atmosphere now composed of over 97% CO2, under pressures nearly 93 times that on Earth. Venus completes one orbit around the Sun in 225 Earth days, but its rotation is peculiar. It spins retrograde, meaning the Sun would seem to rise in the west and set in the east. Even more remarkable, a single Venusian day, the time between two sunrises, lasts about 243 Earth days, longer than its year. Missions such as the Soviet Venera landers and NASA's Magellan orbiter have revealed volcanic plains, massive lava flows, and terrain sculpted by heat, pressure, and chemical weathering. These findings suggest a world both familiar and alien, a crucible of geologic forces sculpted not by water, but by fire and suffocating heat. Mars, the red planet, is a rocky world about 1/10 the mass of Earth, bathed in ochre hues caused by iron oxide dust on its surface. From Earth, it gleams as a reddish point in the sky, a distant neighbor with secrets that have captivated humanity for centuries. But Mars is far more than a colored dot. It is a world shaped by ancient water, wind-blown dunes, towering volcanoes, and a climate in flux. Vast volcanoes dominate the landscape, the most impressive being Olympus Mons, rising over 21 kilometers above the surrounding plains, the tallest known mountain in the solar system. Unlike Earth, Mars lacks active plate tectonics, allowing volcanic structures to grow massive and remain in place. Broad canyon systems like Valles Marineris stretch thousands of kilometers and plunge to depths of over 8 kilometers, evoking dramatic geologic forces at work long ago. Today, Mars's surface is sculpted by dust storms, seasonal ice caps, and the subtle rhythms of a thin atmosphere composed mostly of carbon dioxide at less than 1% of Earth's pressure. Seasonal changes drive sublimation of polar ice, creating winds and global dust storms that can engulf the entire planet. Scientific exploration has transformed our understanding of Mars. The InSight lander, active since 2018, has detected hundreds of Marsquakes, offering clues to the planet's inner structure. Meanwhile, rovers like Perseverance and Curiosity have explored ancient lakebeds and detected complex organic molecules, hinting that conditions suitable for life may once have existed. 2 small moons, Phobos and Deimos, orbit Mars in irregular paths. Phobos creeps downward over time and may one day break apart or impact the surface, while Deimos quietly circles farther out, both relics of past collisions or captured asteroids. Jupiter, the largest planet in our solar system, is a massive gas giant composed mainly of hydrogen and helium. Its immense size, encompassing more than 1,300 times the volume of Earth, makes it a dominant presence in our planetary neighborhood. With strong banded cloud layers and winds reaching hundreds of kilometers per hour, Jupiter's atmosphere is a dynamic and stormy realm. Among its many satellites, 4 stand out: the Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610. These moons are among the most fascinating worlds orbiting any planet. Io is a volcanic powerhouse. Intense gravitational tugs from Jupiter and neighboring moons flex its interior, driving heat that fuels hundreds of active volcanoes, some spewing molten rock hundreds of kilometers above the surface. Europa is shrouded in ice, crossed by dark fractures that hint at a hidden ocean beneath. This saline subsurface ocean, warmed by tidal forces, makes Europa a prime candidate in the search for environments that could support life. Ganymede, the largest moon in the solar system, even larger than Mercury, displays a landscape of ancient cratered terrain alongside younger, smoother regions. Unique among moons, Ganymede generates its own magnetic field, suggesting a dynamic interior. Callisto, the most distant of the 4, preserves a heavily cratered surface that records billions of years of impacts. It, too, is suspected of hiding an ancient ocean beneath thick layers of ice. These moons are not mere appendages of Jupiter. They are worlds in their own right, holding clues about planetary formation, subsurface oceans, and the wider potential for habitable places beyond Earth. Saturn is a planet of elegance and complexity. Known for its spectacular rings, it lies nearly 1.4 billion kilometers from the Sun. Composed mainly of hydrogen and helium, its atmosphere churns with winds and storms beneath a cloud deck of subtle hues and shifting patterns. Saturn's rings are composed of billions of particles of ice and rock, forming a vast, thin disk that shimmers when illuminated by the sun. These rings are not static. They show waves, spokes, and structures shaped by gravitational interactions with nearby moons. Among Saturn's many moons, Titan is exceptional, larger than the planet Mercury and cloaked in a thick, nitrogen-rich atmosphere. Titan hosts lakes and rivers of methane and ethane, forming familiar landforms in a truly alien environment. Beneath its icy shell, data hint at a liquid water ocean mixed with ammonia, raising the possibility of exotic biochemistry. Enceladus, though much smaller, has captured scientists' attention with its geysers of water vapor and organic compounds erupting from the South Pole, evidence of a salty subsurface ocean warmed by tidal forces. Other satellites such as Tethys, Dione, and Rhea reveal ancient cratered surfaces, each telling a story of bombardments and icy geologies. Some, like Hyperion, spin chaotically. Others, like Phoebe, are thought to be captured objects from the distant reaches of the solar system. Explored in detail by the Cassini-Huygens mission, Saturn and its moons have offered scientists a rich laboratory for understanding ring dynamics, moon formation, and planetary processes in a realm far beyond Earth. Far beyond Saturn lie the twin ice giants, Uranus and Neptune, mysterious worlds dominated by materials heavier than hydrogen and helium, ices like water, ammonia, and methane. Uranus orbits the Sun at roughly 3 billion kilometers and is unique in that it rotates nearly on its side, giving rise to extreme seasonal changes over its 84-year orbit. Its atmosphere of hydrogen, helium, and methane gives it a blue-green color, and while Voyager 2 remains the only spacecraft to visit it up close, its tilted orientation and complex magnetic field continue to intrigue scientists. Neptune, even farther out, is a world of violent winds and storms. Its deep blue hue is sculpted by methane and possibly other unknown atmospheric components. Voyager 2's flyby in 1989 revealed an active atmosphere with winds exceeding 2,000 kilometers per hour, mysterious rings, and a host of moons, including Triton, which orbits in a direction suggesting it was captured rather than formed in place. Together, these ice giants challenge our understanding of planetary dynamics, atmospheric physics, and the varied evolution of worlds in the outer solar system. At the fringe of Neptune's family of moons lies Triton, an unusual satellite that orbits in the opposite direction of the planet's rotation, indicating a likely capture from the distant Kuiper belt. With temperatures as low as -235 degrees Celsius, Triton is one of the coldest known bodies, featuring geysers that spew nitrogen gas and possibly organic material from beneath its frozen crust. Voyager 2's exploration revealed Neptune's faint rings and tiny moons, but more importantly, it offered the first close-up look at Triton's active surface. Farther beyond lies the Kuiper belt, a vast region of icy bodies orbiting the Sun at distances beyond Neptune. Among them, objects like Eris and Sedna follow highly elongated orbits and remind us that the solar system continues into realms far beyond the planets we know. Even farther out exists the hypothesized Oort cloud, a spherical reservoir of icy debris that may extend up to 100,000 astronomical units from the Sun. Though never directly observed, its existence is inferred from long-period comets that swoop inward after millennia in deep space. This distant frontier emphasizes the vastness and complexity of our solar system, a place not just of planets and moons, but countless icy worlds still waiting to be understood.